All right, this is Honors Algebra 2 Pre-Calc. We're doing part 3 in 2.7 of Algebra 2, which is still transformation of functions. So this video is going to discuss non-rigid transformations to the parent function f of x. So rigid transformations, which we've already seen, are translations, meaning sliding, or reflections, which is flipping, right? Rigid transformations don't change the physical shape of the graph. Like you could, have a version of the graph written on a piece of clear, like transparency paper, and you could just slide it around or flip it over and it would stay exactly the same. But non-rigid transformations, as the name implies, are not rigid. So that means that they're going to actually change. They're going to stretch and shrink a graph, so it's going to look a little bit different. So we're going to let c be some positive number where c is not 1. The reason that we're saying c is a positive number is if you have a negative number in front of a function, like let's say you had a negative 5, we're going to treat that as two transformations. The 5 is going to be a transformation that is non-rigid, that's going to be a shrink or a stretch or whatever, and the negative is going to be one of those reflections that we've already seen, like a flip, right? So a negative number in front is actually two transformations, a flip and also the stuff that we're covering right now. So as we did previously, we're going to have a discussion about the two different things that could be happening. We're going to have discussions about things that are outside the function, right? So in blue, we have the stuff that is outside the function, right? And those are going to be vertical and logical. So a number c in front of f of x means multiply each y value by c. You're going to leave the x values the same. So if c is bigger than 1, that means that each y value is getting made into a bigger number, right? Because you're multiplying each y value by a bigger number, right? So that's going to be a vertical stretch by a factor of c. For instance, if there was a 2 in front of my f of x, I would double every y value but leave all the x's the same. If there's a number smaller than 1, right, and remember these are all positive numbers, so smaller than 1 but bigger than 0, then what's going to happen is that we're going to get a vertical shrink, or what's also called a compression by a factor of c. So for instance, if there were a 1/3 in front of f of x, I would be multiplying each y value by 1/3, meaning the number will come out smaller. So outside functions, or changes outside the function are logical and vertical, right? We've seen that before. Changes inside the function are horizontal and backwards. So if that c is instead inside f of x, then instead of multiplying by c, what we're going to do is we're going to take each x and we're going to divide each x value by c, right? So meaning like multiply by 1 over c or divide by c. So you're going to leave all the y values the same, but again, it's the opposite of what you would think. You're not going to multiply the x values, you're going to divide them by c. So this means that if c is a big number, dividing by a big number, like a number bigger than 1, right? So if c is bigger than 1, you're actually going to shrink the x value. So that's a horizontal shrink or compression by a factor of 1 over c. But if the c values are smaller than 1, like a half, well, dividing a number by half is the same as multiplying it by 2. It's actually making it bigger. So if the numbers are smaller than 1, then what's going to happen is you're going to have a horizontal stretch by a factor of 1 over c. So we're going to walk through this and see what it looks like. And before we do that, let's talk real quickly about how horizontal and vertical stretches and shrinks are related. So our next slide's actually not a practice problem. Our next slide's going to be talking about sort of the relationship between these using a classic toy from the 1980s that, or maybe early 90s, that my parents and several other parents totally let us use despite it being kind of dangerous and terrifying. All right, so Stretch Armstrong. Is your brain thinking that a vertical stretch and a horizontal shrink seem to be related, right? That if you make the y values bigger, if you make a graph taller, inexplicably it also looks skinnier, or vice versa, if you make a graph shorter, it kind of looks wider. Well, you're not wrong. So it's sort of like the toy Stretch Armstrong. See these lovely pics, right? So this is Stretch Armstrong. Stretch Armstrong was a toy that was like solid rubber and built like a little bodybuilder guy from the 1980s, 1990s, right? And basically the idea was that you and your friend would pull on his limbs, inexplicably, really, really hard. And I don't know what the end game of Stretch Armstrong was supposed to be, but what the end game turned out to be was that one person would let go and the other person would get smacked in the face by like a giant, really heavy rubber doll. So well done, toy company. But it's a good lesson here. So when you pull Stretch Armstrong up and down, right? So somebody's pulling this way and somebody's pulling this way. That's a vertical stretch, right? So what's happening right here is definitely a vertical stretch, right? He's getting taller and skinnier. But as he's getting taller, he's also, because he's getting pulled out, he's getting shrunk in. So a vertical stretch is causing a horizontal shrink, right? So as he gets taller, he's also getting skinnier, right? If you do the opposite thing, right, if instead you pull him horizontally, right, so these kids are pulling this way, right, that's a horizontal stretch, right? But as he gets wider, what you'll notice is he's definitely physically shorter. Like if you count from the bottom of his feet to the top of his head or his arms, which is the highest, that's definitely shorter. So that horizontal stretch caused a vertical shrink. And that's not an accident, right? So if you're thinking, oh, hey, these are kind of related, that's weird, they are related, and it actually ends up making a lot of sense when we look at a graph. Also, as a side note, we legit all know this kid from like 8th grade that left for summer short and a bit heavier and came back to 9th grade like a foot taller and mad skinny. So that kid stretched vertically and by consequence shrank horizontally. And that's the thing that we see a lot. So if you feel like these are related, you're not off task, you're not thinking about it wrong, they are somewhat related. So let's go ahead and walk through some practice problems. So in E5, we're going to go ahead and graph this transformation. So let's graph the original. Hopefully you're getting pretty good at graphing the parent functions, probably better at it than I am at this point. All right, so there's my parent function. So what's going to happen is this 3 in front of this, right, the 3 in front of the parent function is going to be a vertical stretch. That's not how you spell stretch. Okay, by a factor of 3. Okay, so that's what's happening, right? So that's my explanation in words, okay? But let's look at what's actually happening. What's really happening is, so what I need to do this is I need to do 3 times the y values. X's stay the same. Okay, so I'm not changing the x's, I'm doing 3 times the y value. So this y value was 0, it's going to stay 0, because 3 times 0 is 0. But this y value was 1. 3 times 1 is going to be 3. And this y value is 2. 3 times 2 is going to be 6. So what's going to happen is I'm going to get that same square root. Oh, hang on. Sorry, clicked the button. Same square root, but it's going to be stretched. And sure enough, if I put this over here, I put this in on my calculator and graph it, you're going to see that it is physically taller than the original, okay? So that's how a vertical stretch works. So I'm going to let you try a P5, same basic idea, also vertical. And again, you can pause me if you don't want me to do it, but I'm going to go ahead and start doing the problem. So I draw my x squared, which again, we want to get good at those 4 parent functions, and we're going to learn more parent functions as we keep moving forward. Now what this 1/2 is going to do, right? So because this is out in front, right, here's my whole function. This thing is clearly in front. So this is definitely a vertical change, right? And because this number is smaller than 1, this is going to be intuitive. Vertical changes make sense. This is going to be a vertical shrink by a factor of 1/2. That's what's happening, right? So when you're asked to explain what's happening, that's what's happening, right? But what this means that we do is we're going to do 1/2 times the y value, and we leave the x value the same. So it's sort of like, if it's easier for your brain to conceptualize, it's the y value divided by 2, right? So 0 divided by 2 is still 0. 1 divided by 2 is 1/2, so it's half as tall. The same thing's going to be true over here. 4 divided by 2 gives me a 2. 4 divided by 2 gives me a 2. And sure enough, this is a vertical shrink, right? It's like I press down on this graph, right? So it's like I press down on this graph. It's a vertical shrink by half. It is a shorter graph. And you can see this if you want to graph this here too. I didn't actually type this one in, but you can go ahead and type in an x squared, and then I'm just going to do 0.5 because I'm lazy, 0.5x squared, and then you'll see my slightly shorter graph, okay? All right, so let's do some inside changes. So here I have a change that's on the inside, right? This is definitely on the inside. So this is definitely horizontal. Remember that horizontal things are backwards. So you would think that multiplying by 5 would make something 5 times bigger, but horizontal changes are backwards. So this is going to be a horizontal shrink by 1/5. And you can say factor of 1/5 if you want, or you can just say by 1/5. But basically what you're doing, so that's what's happening. And the thing I have to do is I need to take all of my x values and divide by 5. Or times by, like if it's easier to picture in your brain, you take 1/5 times the x value. You don't change the y value. So let's go ahead and plot my original graph. So this is an absolute value graph, so it's going to look like this, sort of. Okay, and I'm just going to pick the bottom points to use for my, okay, so close enough. Okay, it's going to be a little bit beneficial for me since I'm taking the x values and dividing them by 5. It's going to be a little helpful for me to use this value right here that's at 5 and -5 just because they're going to help make my v. So in this particular instance, I'm going to make a point of making those obnoxious dots because I don't really feel like dividing a bunch of things by 5 that aren't divisible by 5. So 0 divided by, so the x coordinate's what changes, the y stays the same, right? Okay, so 0 is the x coordinate, 0 divided by 5 is still 0. The y coordinate stays 0. So if it's easier to see, so let me look at this point. Okay, this point originally, I think the x's are a little harder to conceptualize for people. So this point originally was 5, 5. The new point should have the x value divided by 5 and the y value stays the same. So this point is going to become 1, 5. And this point is going to become -1, 5 because I'm dividing the x coordinate. So what's going to happen is you're going to get a much taller and skinnier v, right? This point was originally 5, 5. And again, the reason I made a point of looking at the points that are 5s was because it's just the easy way to deal with the fact that I didn't want a ton of decimals. But, and I kind of missed, but you get the idea. It's a really skinny v, okay, really skinny v. Now, again, if you wanted to find all those points along the middle, right, let's just look at, we'll look at this point right here, right? Sorry, my bad. Okay, let's look at this point right here. Sorry, there's that little clicky thing on the pen that gets me. This point was originally 1, 1. It's now going to be 0.2, 1 because I'm dividing 1 by 5, right? So, and you can kind of see that that's where that point would be, 0.2, 1. And the same thing here, this is going to end up being 0.4, 2, and 0.6, 3, and 0.8, 4. It's not ideal, but that's the gist. So if we look at what this looks like, now you might say, hey, that's weird, that looks like it's a vertical stretch. Well, that goes back to our stretch Armstrong conversation, right? So math over to number, we want absolute value of x, right? And then for this one, we're going to do math over to number. We want absolute value of 5x. Cool. All right, and there's your graph, and there's the really skinny v. So again, it's not an accident that if you push this graph in from the sides, right? So what's basically happening is you're taking the black graph, right, and you're pushing it in from the sides. Seriously, I hate this stupid clicker on the pen. You're pushing it in from the sides, and when you push those black branches in, it also forces them up, and that's why it ends up looking like the red graph that is a skinnier v, okay? So again, it's a horizontal shrink by 1/5, but it inadvertently also causes a vertical shrink. All right, so, or I'm sorry, a vertical stretch. So now I want you to try P6, and I'll go ahead and try it at the same time, but you're welcome to pause me if you don't want me to. So when I go ahead and graph my square root, it's going to look like this, right? So I see that this is on the inside, right? So I know that that definitely means that it's horizontal, right? So this is horizontal, right? And then it's the opposite of what you'd expect. So timesing by a half should make things smaller, but it's not going to make things smaller. It's going to be a horizontal stretch by a factor of 2, right? Because the reason it's 2 is because it would be 1 divided by 1/2, which is a 1 times a 2 over 1, which is definitely a 2, right? So what that's going to mean is that I do 2 times the x values, and I leave the y values alone. So if it's easier for you to list the points, right? So 0, 0 is going to stay the same because you're multiplying by a number, and that's going to stay the same. But if it's easier for you to list the points, right? So I had the point 1, 1, and I had the point 4, 2, right? So what those points are going to turn into, since I'm multiplying the x by 2, are 2, 1, and 8, 2, right? I'm changing the x value. So 2, 1, and 8. So there's 4, 5, 6, 7, 8 would be here and here. So what's going to happen is it gets pulled out like this. It's like basically like this was locked in place and you pulled this end and made it skinnier, right? But again, notice it also, when you pull that end, I didn't mean skinnier, I meant shorter. When you pull that end and make this thing wider, you're also making the entire graph shorter. So the horizontal stretch by a factor of 2 is also incidentally going to be a vertical shrink of some kind, and that's kind of the gist, okay? So again, that's how these stretches and shrinks work. I'm not going to make you do a ton of really complicated stretches and shrinks or stretches and compressions if you like that terminology better, but that's sort of the idea, is that this graph gets taller or shorter, and it gets wider or skinnier depending on what you're multiplying or dividing by. Remember that if there's a negative in front, which is something we're going to deal with in the next video, then you're actually treating that as two transformations, right? Like a -2 in front of something would be both the 2, which is a stretch of some kind, like if you had 2 in front of f of x, and also the negative, which would be flipping over the x-axis, okay? So that's it for this video.